So I ran out of time to explain a little bit more. I wanted to really emphasize the fact that the maximum a posteriori estimate took this particular form. Why I wrote it in this form rather than just, keeping the original expression here. It looks a little more complicated, but this is really an important concept to understand. So I said this is a convex combination of these 2 points, and to drive home, or to explain what I mean by that, if you don't know what that term means, a convex combination of points x and y, just some for any points. They could be, they could be vectors or real values or whatever, is some real number alpha times x plus 1 minus alpha times y for some real number alpha between 0 and 1. Could be 0 also, or 1. So what this is doing, a convex combination, so if this is x and this is y, they're just maybe in some points in some vector space or something, then all the set of these convex combinations are the points which linearly interpolate between x and y. That's supposed to be a straight line. So it's all the points on the straight line from x to y. As alpha varies from 0, if alpha is, say, 1, then you start out here at x, and as alpha decreases down to 0, you move over to y. So the nice thing about writing the map in this way is that you can think of the map as being sort of like the sample mean. So it's a special case of the sample mean. If, for example, let's see, so if n, let's see, if, so let's say it this way. So if, I guess it's not strictly speaking a special case in this case because, if sigma squared were 0, then this would be 0, and this would be n over n, which is 1, and you would get the sample mean. But, technically speaking, we should have a strictly positive variance. But you can think about sort of in the limit as the variance goes to 0, that the sample mean, which is, by the way, which was the MLE, right? Remember, if you remember that this was the MLE, I should emphasize that. This was the MLE, and you can think about this as the MLE is sort of a special case of the map. And furthermore, using this convex combination interpretation, as n and sigma squared sort of vary, then you're getting a range of values between the sample mean and the prior mean. Right? So if our prior mean was here, say, and we got a sample mean over here, then as n and sigma squared vary, then our posterior, or rather our map estimate, is going to be somewhere in this range. And so, let's see. So if as n goes to, what do we want n to do? If we wanted to recover mu, then if n was, so if n was 0, if we have no data, right, that makes sense. If we have no data, then this is 0, so this drops out, and this just becomes 1 times mu. So if we have no data, so when n is 0, we start out at mu, and as n goes to infinity, if n is very, very large, then this goes to 0, and this goes to 1. So as n goes to infinity, we're approaching the sample mean, which is the MLE. So it's this type of representation as a convex combination of the prior and the sample mean, it turns out that this is actually a fairly general thing for the map estimate. very often that it turns out to be a convex combination of the prior and well, more generally the MLE. And this is where a connection with, well, this is where you can really see a connection with the some very closely related concepts called regularization and shrinkage. So shrinkage looks a lot like this. It's essentially the same thing, and so does regularization. So I just wanted to emphasize this very important interpretation of sort of understanding how, what the map is doing in relation to the prior and the MLE.